Have you ever really stopped to think about the sheer raw power it takes to run the AI tools we use every single day? We're talking about computational muscle on a scale that is just, well, it's almost unimaginable, and it's all built on decades of innovation. So let's get into it. So what does it actually take to build that future, right? It's not just about some clever software or, massive data sets. The story here is so much deeper, and it really starts with the very foundation of computing itself. In fact, this whole story kicks off with a custom-designed piece of silicon and a simple back-of-the-envelope calculation that, about a decade ago, literally terrified Google. This one calculation revealed a crisis that threatened to stop their entire AI progress dead in its tracks. Now, to really understand that crisis, we first have to look at the solution they've come up with today, a brand new, absolutely cutting-edge AI superchip. This right here is the 7th generation of Google's custom chip, the Tensor Processing Unit, or as you'll hear, the TPU. Now, according to Google's chief scientist, Jeff Dean, every new generation is a big leap forward. But what really makes this one so special? Well, for starters, they don't just use one. No way. They connect thousands of them into these massive supercomputers that they call pods. And get this, we're talking about over 9,000 of these new chips, all linked together in a single system. That is an incredible amount of focused AI power. So, what can these new pods actually do that's different? Well, the new TPU is basically optimized for the very specific kind of math that powers modern AI. This means much faster training for these giant models and way more efficient inference, which is just the fancy word for when an AI makes a prediction or generates a response for you. Basically, it's all about being faster and smarter. Okay, so this amazing hardware didn't just appear out of thin air. There's a really good reason for it. To understand why Google went through all the trouble of designing its own chips from scratch, we have to rewind and go back to the problem that started this whole journey. And this really gets to the scale of the problem. Back in 2013, Jeff Dean ran some numbers for a new, much better speech recognition model. And when he saw the results, he realized that to serve this one feature to about 100 million users, they would have to literally double the size of all of Google's data centers. Just think about that. A truly scary thing. So yeah, that scary calculation in 2013 kicked off an absolute race against time. By 2015, the very first TPU was deployed in their data centers, solving that immediate crisis. And that spirit of innovation has just kept going, leading us all the way to today's 7th generation powerhouse. This whole thing was a response to what was basically an existential threat to their AI ambitions. And the results, even for that very first version, were just staggering. The first TPU wasn't just a little bit better. It was 15 to 30 times faster than the CPUs and GPUs they were using at the time. And here's the kicker. It was a mind-blowing 30 to 70 times more energy efficient. That just fundamentally changed the entire economic equation of doing AI at scale. But this was never just about building a faster chip. The real secret sauce here is the deep, deep connection between the hardware and the software that runs on top of it. This brings us to a really critical concept called hardware/software co-design. So instead of building a generic one-size-fits-all chip, Google designs its TPUs specifically for the kinds of AI models they think they'll want to run 2, 3, maybe even 5 years from now. It's kind of like building the racetrack and the race car at the exact same time, so they're perfectly matched. And what this does is it creates this incredibly powerful feedback loop, this virtuous cycle. The AI researchers dream up new, crazier models, and that tells the hardware team what capabilities they need to build into the next chip. Then, that new, more powerful hardware lets the researchers create even bigger and more capable models. See? Each side just keeps pushing the other one forward. But hang on, where do these big ideas even come from in the first place? This whole technological stack, from the custom silicon all the way up to these massive AI models, it's all built on a foundation that's actually much older and much, much broader. The truth is, today's AI revolution didn't just pop into existence. It really is standing on the shoulders of giants. And specifically, we're talking about decades of fundamental academic research, a lot of which was funded by public institutions. I mean, Jeff Dean himself points out that Google as a company was built on this kind of research. The very protocols that run the internet, the design of modern processors, even the PageRank algorithm that started Google, it all came from academic projects. And the core ideas of modern AI, things like neural networks and backpropagation, are actually 30 or 40 years old. And this is exactly why having a healthy research ecosystem is so critical. It needs different kinds of support, too. Everything from traditional government grants that fund that foundational early-stage science to newer alternative models that fund ambitious, multi-year moonshot projects that are focused on solving very specific, real-world problems. So what does one of these ambitious moonshots actually look like in practice? Well, Jeff Dean is particularly passionate about one area where all this power could make a really profound difference: healthcare. And this is the grand vision he lays out. Just imagine a world where every single diagnosis, every treatment, every outcome from the past could be used to help doctors and patients make better decisions today. I mean, that is an incredibly powerful and just plain inspiring goal for AI. And this approach is such a stark contrast to a lot of the vague hype we hear about artificial general intelligence, or AGI. Instead of chasing some distant sci-fi dream, the moonshot approach is all about focusing on tangible, achievable goals within a 3 to 5 year window. It's about making a real, measurable impact on people's lives right now. Of course, getting there is not going to be easy. The challenges are immense. You've got massive technical hurdles like preserving privacy, the really grungy but absolutely essential work of cleaning up messy data, and then you have to navigate this whole maze of legal and policy issues. It's a problem that requires experts from a ton of different fields all working together. And that really brings us to the final question. We've gone from a custom silicon chip born out of a crisis to the academic bedrock of innovation, all the way to a tangible moonshot in healthcare. It's so clear the power of AI is immense. So as we look to the future, if we can overcome these kinds of hurdles, what's the next great challenge? The next ambitious goal that we should aim for? What's the next moonshot?